November 17th, 1903. The Allegheny Iron Works stands silent in the Pennsylvania darkness. Third shift ended 2 hours ago. The furnaces have been cooling since 6 o'clock. Night watchman Thomas Brennan makes his rounds through empty corridors where the air still holds the day's heat. It is 11:47 p.m. when the world inverts. Brennan will later tell investigators he felt the sound before he heard it, a pressure change that made his ears pop. The floor beneath him seemed to drop and rise in the same instant. He ran toward the boiler house not because he understood what had happened, but because something in the quality of that sound demanded witnesses. What he found made no sense. The number 3 atmospheric condenser, a sealed iron cylinder 12 feet tall and 6 feet in diameter, had ceased to exist as a coherent object. But the room around it showed none of the expected signs. No scorch marks on the brick walls. No outward blast pattern. The heavy iron door to the chamber hadn't been blown off its hinges. It had been sucked inward, hanging now at an impossible angle, its hinges bent toward the interior. Brennan later testified, "I thought at first I'd gone to the wrong room. Couldn't make sense of the geometry. The metal was everywhere, but it was all pointed wrong, like something had reached up from below and pulled." By midnight, Superintendent James Hartley arrived from his home 3 miles away. By 12:30, the local fire brigade had confirmed what seemed impossible. There had been no fire. By dawn, engineers from Pittsburgh were standing in the wreckage, and none of them could explain what they were seeing. The furnace had exploded without burning. First light revealed the true scope of the contradiction. The condenser vessel itself had fragmented into 17 major pieces and countless smaller shards, some no larger than a playing card. The fragments lay in a rough circle around the vessel's original position, but the distribution pattern violated every principle of explosive force. Chief Inspector William Morrison documented the scene with a methodical precision that would later prove crucial. Morrison would later recall, "The largest fragments were furthest from the center, yes, but they had fallen almost straight down, as if dropped rather than thrown. Smaller pieces near the base of the unit showed crushing damage, not tearing. The metal had failed under compression, not tension. The brick foundation that had supported the condenser showed no blast cratering. Instead, the bricks were fractured in a pattern Morrison had seen only once before, in a building collapse where weight had exceeded structural capacity. But the condenser weighed 4 tons empty. The foundation had been designed for 6. The temperature of the metal fragments told its own story. At 6 a.m., more than 6 hours after the event, engineer David Woolsey measured the surface temperature of the larger pieces with a pyrometric crayon, 82 degrees Fahrenheit, the same temperature as the morning air. Woolsey testified, "I checked it 3 times, had another man verify. We were looking for residual heat from combustion or friction. There was none. The metal was cold." More troubling still was the interior surface of the fragments. Where the vessel's inner wall was exposed, condensation had formed, small beads of water that caught the early light. Inside a sealed chamber that had catastrophically failed, moisture was appearing as if the iron itself were weeping. The room's walls told a story that contradicted explosion in its conventional sense. Dust patterns on the brick showed movement toward the condenser's location, not away from it. A wooden tool rack mounted 6 feet from the vessel had been pulled partially free of the wall, its nails bent toward the point of failure. The glass panes in the chamber's single window had blown inward, littering the floor with fragments that crunched under the investigator's boots. Assistant Foreman Patrick O'Neill had been the last man to see the condenser intact. He had locked the boiler house at 6:15 p.m., following standard shutdown procedure. O'Neill stated, "Everything was nominal. We'd run the cooling cycle by the book, closed the steam inlet, opened the drain valve for the water jacket, sealed the main chamber. Temperature was dropping steady, maybe 240 degrees when I left, nothing to suggest trouble. Nothing visible, at least. But in the 17 hours between O'Neill's departure and the moment of failure, Something had transformed the condenser from a functional component of the ironworks' atmospheric system into a weapon primed against itself. The question that faced Morrison and his team was simple to ask and seemingly impossible to answer. What force could destroy a pressure vessel this thoroughly while leaving no evidence of heat, combustion, or explosive chemical reaction? The first theory emerged before the sun had fully risen: gas explosion. It had the virtue of simplicity and the weight of precedent. Industrial accidents in 1903 were frequently the result of coal gas accumulation, and the Allegheny Works used gas lighting throughout its facilities. Inspector Morrison assigned 2 men to test the hypothesis. The examination of the condenser fragments revealed no sooting, no carbon deposition, no sulfur staining. The characteristic rainbow sheen of a gas fire on iron surfaces was absent. More conclusively, the atmospheric sensors in the boiler house, primitive but functional devices that used flame deflection to detect combustible vapors, showed no unusual readings in the hours before the failure. The logbook confirmed they had been checked at 6 p.m. and again at 9 p.m. by the night supervisor. Night Supervisor Jenkins recorded, "Both lamps burned steady and blue. Any gas present would have showed as yellowing or flickering. I noted it in the log as standard." By mid-morning, the gas explosion theory was abandoned. The evidence simply wasn't there. The second theory was more disturbing: sabotage. Labor tensions in the steel industry had produced violence before. Only 8 months earlier, a furnace in Ohio had been deliberately damaged by disgruntled workers seeking to disrupt production. Could the condenser have been tampered with? The vessel's access points were examined for signs of forced entry. The inspection hatches showed no tool marks. The seal on the main chamber was intact until failure. The valve stems bore no evidence of recent adjustment beyond normal operation. Moreover, the timing argued against human intervention. The night shift had ended at 9:45 p.m. The explosion occurred 2 hours later, with the facility locked and under the watch of Brennan, whose rounds were documented by a time clock system at 12 stations throughout the works. Hartley later explained, "We pulled the time clock records. Brennan was in Building 7 when the condenser failed. That's 300 feet away with 3 locked doors between. Nobody else had access. The sabotage idea died quick." By the afternoon of November 18th, Morrison faced an increasingly skeptical audience. The Pennsylvania Industrial Safety Commission had sent an observer. The insurance companies had sent their own investigators. The newspapers were calling it the mystery of the midnight blast, and Morrison had no explanation that fit the evidence. Morrison admitted years later, "I've investigated 37 industrial failures. Everyone had a clear mechanism. Boiler ruptures show tearing from internal pressure. Structural collapses show fatigue cracking. Gas explosions leave chemical signatures. This showed none of it. We weren't just missing the cause, we were missing the category of cause." That evening, Morrison made a decision that would later be recognized as the turning point of the investigation. Instead of continuing to search for what had happened, he began to systematically document what hadn't. Morrison's list grew over 3 days of meticulous observation. Each negative finding narrowed the field of possibility, eliminating entire categories of failure until only the inexplicable remained. No thermal damage. The bricks surrounding the condenser location showed no discoloration from heat exposure. Paint on nearby iron pipes was intact. Wood framing in the ceiling above the unit was unmarked. If combustion had occurred, it had burned cold, a physical impossibility. No overpressure burst pattern. When a vessel fails from internal pressure, the fracture propagates along stress lines in a characteristic pattern. The metal tears outward, creating jagged edges with directional indicators. Morrison examined 143 fragment edges using a magnifying lens. The failure surfaces showed compression failure. The metal had been crushed inward before fragmenting. Metallurgist Dr. Henry Patterson was brought in from Carnegie Steel to examine the fragments. His testimony would become crucial. I've seen this kind of damage in structural beams that have been overloaded in compression. The iron doesn't tear, it crumbles. But a pressure vessel failing from the inside should never show this pattern. The pressure acts outward, putting the wall in tension. These fragments had been in compression. No chemical residue. Samples of the debris were analyzed for explosive compounds. Nitrates, chlorates, phosphorus, sulfur compounds, all absent. The iron showed no chemical alteration beyond normal oxidation. Whatever had destroyed the condenser had left no molecular signature. No witness to build-up. The time clock records placed Brennan within 200 feet of the boiler house for his entire shift. His rounds brought him past the chamber door every 37 minutes. He reported no unusual sounds, no hissing of escaping steam, no vibration in the floors or walls. The destruction, when it came without warning. No structural defect. The failed condenser had been manufactured by Harrison Brothers of Philadelphia in 1897. It had been inspected annually, most recently in August of 1903. The inspection report noted minor scale buildup, but found the vessel sound. Thickness measurements showed the iron walls were still well within tolerance. The unit had no history of malfunction or repair. Morrison's deputy, a young engineer named Robert Callahan, summarized the contradiction in his notes. We have a vessel that destroyed itself with the force of high explosives, but contained no explosives. That failed from the inside, but shows external compression damage. That released tremendous energy, but remained cold. That burst without warning, but gave no sign of stress. Every piece of evidence contradicts every other piece. By November 21st, 4 days after the failure, Morrison had documented everything the incident was not. He was no closer to understanding what it was. Then David Woolsey found the water. Woolsey was examining the condenser's drain valve system when he noticed something that had been overlooked in the initial documentation. The drain valve, a simple gate valve designed to empty the water jacket surrounding the condenser chamber, was closed. According to O'Neill's testimony, he had opened it during shutdown procedure. The logbook confirmed this. At 6:15 p.m. on November 17th, O'Neill had noted, "Drain valve opened, water jacket emptying." But the valve Woolsey examined was in the closed position, and the stem showed no sign of having been forced. The valve had been closed deliberately, by hand, sometime after O'Neill left. Hartley reviewed the access logs. Only 3 people had keys to the boiler house: O'Neill, Jenkins, and Brennan. Jenkins had been off-site that evening. Brennan's rounds were accounted for. O'Neill had gone home directly after locking up. The valve had closed itself. Patterson, the metallurgist, examined the valve mechanism. The stem was threaded iron, the seat was bronze, the handle was cast iron. Standard construction for the period. But the stem showed unusual wear, a pattern of microabrasions consistent with rapid rotation under load. Patterson's analysis raised more questions than it answered. The stem rotated backward, clockwise, which closes the valve. But there's no mechanism for that. No spring, no counterweight, no pneumatic operator. For this valve to close itself, something had to turn it, and turn it with considerable force, given the friction in the stem threads. Morrison ordered the water jacket drained and examined. What they found was a chamber that should have been empty, but contained approximately 40 gallons of water. The water was cold, the same temperature as the November air, but its presence violated procedure and logic both. The condensation on the inner wall fragments now took on new significance. Morrison assembled the larger pieces of the vessel's inner chamber in approximate position on the boiler house floor. The condensation pattern was uniform, a thin film of moisture covering every exposed surface. The film was thickest near the bottom of the reconstructed chamber, thinning toward the top. Woolsey proposed a hypothesis. What if the condenser wasn't empty when it failed? What if there was water inside the sealed chamber? But where would the water come from? The condenser operated on a closed-cycle atmospheric system. Steam entered the chamber, condensed on the cooled walls, and drained through collection tubes. During normal operation, the chamber never flooded. The drain system prevented accumulation. During shutdown, the chamber was sealed empty at elevated temperature to prevent condensation during cooling, unless the seal had been compromised during operation. Morrison examined the chamber's main seal, a ground iron joint with a gasket of compressed asbestos paper. The seal showed no sign of leakage or deterioration, but the mating surfaces showed something unexpected, a microscopic deposit of iron oxide, the characteristic red-brown of rust, in a pattern suggesting repeated wetting and drying. The seal had leaked, not dramatically, not enough to affect operation, but persistently. Over weeks or months, moisture had been seeping into the sealed chamber at high temperature, evaporating immediately in the steam-filled interior. During operation, this was invisible. The leaked water simply became part of the steam cycle. But during shutdown, with the chamber sealed and cooling, the physics changed. Patterson began sketching calculations on a chalkboard in the superintendent's office. Steam at 240 degrees Fahrenheit has a certain volume and pressure. Cool that steam without adding or removing material, and it begins to condense into liquid water. Water occupies approximately 1/16 the volume of its vapor. As the condenser cooled through the evening of November 17th, the small amount of water vapor trapped inside would have begun to condense on the iron walls. And as it condensed, it would have created a vacuum. Morrison brought in Daniel Forsyth, a professor of mechanical engineering from Lehigh University, to verify Patterson's calculations. Forsyth arrived on November 24th with a slide rule, a stack of reference texts, and a reputation for ruthless precision. He spent 2 days measuring the condenser fragments, examining the valve mechanisms, and reviewing the operational logs. On the evening of November 26th, he presented his findings to Morrison, Hartley, and the assembled investigators. The condenser chamber, Forsyth calculated, had an internal volume of approximately 170 cubic feet. During normal operation, this space contained steam at near atmospheric pressure and 240 degrees temperature. When O'Neill sealed the chamber at shutdown, it contained this steam plus an unknown quantity of water vapor that had leaked through the seal. As the chamber cooled through the evening, the steam condensed. Forsyth's calculations suggested that if the chamber contained even a few gallons of water in vapor form, its condensation would reduce the internal pressure dramatically. The chamber would develop an internal vacuum measured in inches of mercury below atmospheric pressure. At first, this vacuum would be mild. The chamber had been designed to withstand some degree of external pressure. But as cooling continued, as more steam condensed into liquid, the vacuum would deepen. Forsyth wrote a number on the chalkboard, 14.7 pounds per square inch, atmospheric pressure at sea level. The condenser's external surface area was approximately 565 square feet. That meant the atmospheric pressure acting on the outside of the vessel exceeded 1.2 million pounds of force. Against this, the vessel had been designed to resist perhaps 50,000 pounds of external pressure, more than adequate for normal atmospheric variations. But if the internal vacuum deepened enough, if the pressure differential exceeded the vessel's structural capacity, the iron would fail not from internal explosion, but from external compression. The chamber would implode. Morrison asked the question everyone was thinking. Would an implosion generate the force we observed? The sound, the fragmentation, the distribution pattern? Forsyth's answer was precise. When a vacuum vessel fails, the collapse is not gradual. The iron holds until it yields, and then it yields catastrophically. The walls accelerate inward under atmospheric pressure, reaching considerable velocity before they meet at the center. When they collide, the kinetic energy converts to shock, to sound, to fragmentation. The energy source is the atmosphere itself, 7 pounds per square inch acting over hundreds of square feet. The total energy release would equal several pounds of dynamite. But the energy wouldn't present as an explosion. It would present as an implosion followed by rapid equalization. Air would rush inward through the forming cracks, creating the pressure wave Brennan felt. The fragments would be thrown outward not by internal pressure, but by the collision at the center, like a hammer striking an anvil, with the fragments as sparks. The cold metal, the inward bent door, the crushed foundation bricks, the compression failure of the iron, every piece of evidence suddenly aligned with a single explanation. Woolsey raised the final question. What closed the drain valve? If the water jacket had drained as intended, the chamber would have cooled more slowly, and the vacuum might not have developed. Forsyth examined the valve mechanism again. Then he examined the water jacket itself, the gap between the chamber wall and the outer shell where water circulated for temperature control. The jacket was designed to drain by gravity through the bottom valve, but the jacket also connected to the chamber through small weep holes intended to prevent air pockets. Forsyth's conclusion was disturbing in its simplicity. As the chamber developed vacuum, it began pulling water through the weep holes from the jacket. The flow was enough to create a siphon effect. Water flowing backward through the drain valve, from bottom to top, would create rotational force on the valve stem. The valve closed itself, sealing the water jacket and isolating the chamber. After that, the vacuum had nothing to prevent its deepening. The condenser had destroyed itself through a cascade of failures, each one making the next inevitable. A slow seal leak allowed moisture into the chamber. Shutdown cooling condensed that moisture, creating vacuum. The vacuum pulled water from the jacket, closing the drain valve. The closed valve isolated the chamber, allowing the vacuum to deepen unchecked. When the iron finally yielded, atmospheric pressure crushed it with the force of an artillery shell. And because the energy came from outside rather than inside, because the failure mode was compression rather than tension, the destruction appeared to contradict every principle of explosive force. Morrison filed his final report with the Pennsylvania Industrial Safety Commission on December 3, 1903. The report was 16 pages long, supported by 42 pages of calculations and 31 photographs of the debris field. Its conclusion was unambiguous. The number 3 atmospheric condenser at Allegheny Iron Works failed due to condensation-induced vacuum collapse. The failure mechanism involved 4 distinct phases, each one amplifying the conditions that led to catastrophic structural failure. Phase 1. Chronic seal degradation. The chamber's main seal developed a microscopic leak, allowing water vapor to enter during operation. At operating temperature, this vapor was invisible and caused no immediate malfunction. Over an estimated period of 3 to 6 months, the leak persisted undetected. Phase 2. Shutdown cooling. When the chamber was sealed at 6:15 p.m. on November 17th, it contained steam at elevated temperature plus accumulated water vapor from the seal leak. As the chamber cooled, the vapor condensed on the iron walls, reducing internal pressure. The condensation rate accelerated as temperature dropped, creating an increasing vacuum. Phase 3. Siphon closure of drain valve. The developing vacuum pulled water from the surrounding jacket through the design's weep holes. This reverse flow generated sufficient force to rotate the drain valve stem, closing the valve and sealing the water jacket. With the jacket sealed, the chamber's cooling rate decreased, but the vacuum continued to deepen. Phase 4. Structural collapse. At approximately 11:47 p.m., the pressure differential between the chamber interior and external atmosphere exceeded the vessel's compressive strength. The iron walls failed simultaneously at multiple points. The walls accelerated inward under atmospheric pressure, colliding at the center with sufficient force to fragment the iron and generate the observed shock wave. The total energy release was equivalent to the detonation of 8 to 10 pounds of dynamite, but the energy source was external atmospheric pressure rather than chemical explosion. Morrison's report included recommendations that would change industrial practice. All sealed cooling vessels should include vacuum breakers, simple check valves that allow air to enter if internal pressure drops below safe levels. Drain valves on water jackets should be replaced with self-locking designs that cannot close under reverse flow. Seal inspections should include leakage testing, not just visual examination. But the report's final paragraph addressed the deeper implication. The failure at Allegheny demonstrates that explosion and implosion, while opposite in mechanism, can be identical in outcome. The vessel was destroyed as thoroughly as if it had contained gunpowder. The energy release was comparable. The danger to personnel was equivalent. Yet no fuel was consumed, no flame was kindled, no combustion occurred. The atmosphere itself became the weapon, and the vacuum the trigger. Engineers must understand that external pressure can be as destructive as internal pressure, and that the absence of heat does not imply the absence of danger. By January of 1904, Morrison's findings had been distributed to foundries and manufacturing facilities across the northeastern United States. The Pennsylvania Commission mandated vacuum breakers on all atmospheric condensers. Similar regulations followed in New York, Massachusetts, and Maryland. Between 1904 and 1910, 12 additional vacuum collapse incidents were identified and prevented by the new safety systems. The failures would have been identical to Allegheny, violent, seemingly inexplicable destructions of sealed vessels that had cooled improperly. The vacuum breakers vented the developing vacuum before it could reach dangerous levels. The vessels survived. Thomas Brennan remained night watchman at Allegheny Iron Works until his retirement in 1921. In interviews near the end of his life, he recalled the night of November 17th with a clarity that suggested the memory had never faded. Heard men say it was like an explosion. That's not right. An explosion pushes. This pulled. Even standing 200 feet away, I felt it pulling at me like the air was being sucked toward the boiler house. And the sound, people who weren't there can't understand the sound. It wasn't a bang. It was deeper than that, like the building's bones were breaking. After 40 years of foundry work, I knew every sound metal could make. This was a sound I'd never heard. The sound of iron surrendering. The number 3 condenser site was cleared and filled with concrete. The space was converted to storage. By 1920, most of the men who had witnessed the failure were dead or retired. The incident faded from institutional memory, preserved only in Morrison's report and the engineering literature it influenced. But the fundamental principle remained. A furnace need not burn to explode. A vessel need not contain pressure to burst. The forces that destroyed the Allegheny condenser were present in any sealed chamber that cooled without atmospheric compensation. The danger was invisible, silent, and absolute. The atmosphere weighs 14.7 pounds on every square inch of every surface at sea level. We do not notice this weight because the pressure is equalized. Air inside and outside, pressure balanced. But remove the internal air, create a void, and the weight becomes force. The force becomes violence. The condenser at Allegheny Iron Works did not explode. It was crushed by the weight of the sky, pulling itself apart in the process. The distinction is technical but fundamental. We live at the bottom of an ocean of air, and that ocean, given the chance, will rush in to fill any void with the force of falling stone. The furnace exploded without burning because the explosion was never inside it. The explosion was the atmosphere, claiming back the space that vacuum had briefly stolen.